Hello everyone, welcome to my channel. If you are new to my channel, please subscribe to my YouTube channel, so you can join our tech family. If it is informative to you, please like our video, share it with your friends so they can get help with these video, and don't forget to press all notification bell icon so you get regular update and don't miss any single video.
So tell me what you think. Is it better to have a large network or a few smaller networks? This is a question that you're going to face eventually, if you haven't already. And at some point, you're going to realize that, in many cases, it's easier if you cut up a network into smaller parts. Maybe you'll be doing this for security, or to make it easier to manage. In any case, a critical piece of the puzzle that you'll need to use is the VLAN. And that's the core of this video. We're talking about what VLANs do, and why we use them. We've talked about LANs, or local area networks, before. The trouble with LANs is that it's hard to define what they are. To some people, they are the entire network in a building. To others, LANs are part of the network connected with routers. For this video though, we're going to define a LAN as a layer 2 broadcast domain. You'll probably remember from the last video that we talked about a broadcast frame with the destination MAC address of all Fs, and it will go to all devices. Switches and bridges will forward these frames out, routers will receive them, but they won't pass them on. This, as a whole, is our layer 2 broadcast domain, and for this video, that is what we're calling a LAN. And we're using the symbol here, with devices connected to it, to represent each LAN. As I said earlier though, we might want to cut this up into smaller networks. Take this network for example, where everything is on one single LAN. Maybe this isn't suiting our needs. Maybe the servers have sensitive information on them and should be kept separate from the rest of the network. So, one thing we can do is to cut this into 2 separate LANs. We can keep our servers on one LAN and everything else in the other LAN. If we want, we could even put a firewall between the 2 networks. We haven't talked about firewalls yet, but no doubt you've heard of them. They're security devices which we can use to permit or deny different types of traffic. So by creating 2 different LANs, we can put a firewall in between, and now we're in control of the type of traffic that goes between the regular network and the server network. We'll have a look at creating these permit and deny rules in a few videos' time, but for now, we're focusing on how to break one LAN into smaller LANs. So, how can we do this? How do we break up a LAN into smaller LANs? Well, an obvious solution is to buy an extra switch. The regular LAN can use one switch, and the server LAN can use the other. They can be joined together with another device such as a router or a firewall in our example. The problem is that this is often expensive, especially if we want to create lots of LANs, not just 2. Fortunately, we can create virtual LANs, also known as VLANs, on our switch. Think of this as if you've got a few different switches inside that one box. Some of the ports will be part of one VLAN, while other ports will be part of a different VLAN. And I want to be forthright with you here and say that everyone has troubles understanding VLANs to start with, and that is completely fine. I think that it will make more sense over time as you use them more often. So don't worry too much if you don't get all of this right away. You will definitely get there and it will all make sense. I won't spend a lot of time on this, but there are a few other reasons why we might use VLANs. We've already spoken about security and removing the need for buying more hardware. Another thing we can do is separate devices by their functions. This can be a tool in making management easier. We could also use this to separate a guest network for office visitors, or perhaps a separate network for each department in the office. But we could also use it to separate certain types of traffic. For example, we can have a data VLAN for regular traffic and a completely separate VLAN for voice traffic. This way, we can apply different settings to each VLAN, which we can use to commit different resources depending on their need. We can also limit broadcasts and flooding with VLANs. We'll see more on this soon, but as each VLAN is a separate network, we can restrict traffic to a single VLAN only, rather than letting it flood everywhere. This is also a way of creating smaller failure domains. Say something goes wrong on one VLAN. It depends on the failure, but the problem may be restricted just to that one VLAN rather than spreading to the entire network. If you can think of more reasons you may want to use VLANs, put them in the comments below. So now let's take a few moments to try to understand how VLANs work under the hood, and a bit later on, we'll put it into practice in a lab. Each VLAN has an identifier. This ID is just a number that's used to identify each VLAN. This ID is a 12-bit number ranging from 0 to 4095. However, IDs number 0 and ID number 4095 are both reserved, so our usable range is from 1 to 4094. Each port on a switch is assigned to a different VLAN by using this ID. And when we add VLANs to a switch, we change the broadcast domain. If a broadcast frame arrives on a switch port, it will be sent out all other ports in the VLAN. But it will not be sent to ports in other VLANs. And the same is true with flooding. If a frame needs to be flooded, it will only be flooded on ports within that VLAN. And with less flooding, we reduce our security risk. VLANs are a switching technology, which operate at layer 2. But as you know from the OSI and TCP/IP videos, there are other layers in the network that need to interact with each other. IP addressing, for example, is a layer 3 technology, but IP addresses and subnets still interact with VLANs. Typically, you would have one subnet per VLAN. This is not a technical requirement. You could have devices from different subnets in a single VLAN, but this is considered poor form as we like nice boundaries between our networks. So try to remember this best practice. One subnet per VLAN. When it comes to VLANs, Cisco do a couple of things a little differently to the standard. Mostly just things from the old days that have hung around. So the VLAN range is from 1 to 4094. But on many of their switches, Cisco reserve VLANs 1002 to 1005 for compatibility with their older equipment. Also, Cisco break the VLAN space into two ranges. These are normal and extended. Their original switches only supported the normal range, with the extended range being added later. Inside some of their switches, the normal range is handled a little bit differently to the extended range. Also, Cisco used technologies like VTP, which handle these ranges differently. This is something we're not going to cover in this series, but if you continue on to do Cisco's ICND2 exam, you will come across this technology. We'll also see in the next video that some of Cisco's terminology is also very different to everyone else. I think there might be a question in the back of your minds. How do we get devices on different VLANs to talk to each other? After all, some separation is good, but we still have a network to run and we still need communication. And that is a good question. In most cases, we will need to allow some traffic between devices in different VLANs. If you know your OSI and TCP/IP models well, it's going to pay off for you now. I've said this before, but it bears repeating. VLANs are a switching technology, and they live at layer 2. They provide a layer 2 boundary, and frames from one VLAN will not pass through to another VLAN. So we can use technologies in other layers to help, and this is where layer 3 comes in. Layer 3 is all about IP addressing and moving packets from one network to another, and this is what routers are made for. Each VLAN should be associated with only one subnet. The router has an interface connected to each VLAN, and each interface is connected with an IP address from that subnet. Devices in each network will configure their default gateway to be the IP address of the router. When a device needs to send a frame outside of its local VLAN, it will send the frame to the router using the MAC address of the router as the destination address. The router, as it is connected to both networks, will know where to send the frame. So it will rewrite the destination address field with the MAC address of the destination device, and then it will forward the frame on. This has been a quick refresher of some of the previous videos, so if you want to have a look in more detail again, take a look back at the cabling devices video. And you may be wondering at this point, how do the devices and the router know which IPs match up to which MAC addresses? After all, they have to work with both of these. This too is a very good question. The short answer is that they use a protocol called ARP, or Address Resolution Protocol. We'll go into the details of how this works in a few videos' time, but basically, the devices broadcast an ARP message asking who owns a particular IP address. If the owner is in the local network, it will respond with its MAC address. Don't worry too much if this is not making a lot of sense yet. I'll explain this one in a bit more detail in a few videos' time. But before we move on, take a moment to challenge your understanding with these 5 questions. Don't just go straight for the answers though. Try to work them out for yourself. And now it's time to see it in action. And this is our topology. What we have here is 2 different ways to view our lab network. On the right, we have the physical diagram. As the name suggests, this describes how our network physically connects together. It includes details like the devices used, in our case a single physical switch, and the ports that the cables connect to. On the left is our logical diagram. Now that we're using VLANs, there's a lot happening inside the switches that we can't physically see. So we use a separate logical diagram to explain what's happening internally. From these 2 diagrams, we can see that we have 2 workstations on VLAN 10 and 2 servers on VLAN 20, and a router joining the 2 VLANs. So in this lab, we're going to configure VLANs 10 and 20 and put all of these devices inside them. To start with, the interfaces that the router's connected to will be left disabled. We'll do this so we can truly see the traffic separation. And eventually, we'll enable it so we can see routing between the 2 VLANs. As always, parts of this lab are pre-configured to save time. Lab files are downloadable for the channel supporters. I recommend downloading the lab or building it from scratch so you can try it out yourself. Our first step is to jump onto our switch and create our VLANs. The VLAN ID is the important part here. We can optionally give each VLAN a name, but this is just for organizational purposes. It's not mandatory. If we want to see the VLANs we've created, we use Show VLAN Brief. This shows us all the VLANs on the switch, including the ones we've just created. This includes the VLAN IDs, their names, statuses, and the ports that use them. Notice that there are a few extra VLANs. These include the reserved VLANs that we've already talked about. It also includes VLAN 1, which is always there by default, and VLAN 2, which my lab software created on its own for some reason. But for VLANs to have an effect, we need to add in a few interfaces. To do this, we start by entering interface configuration mode. VLANs are set with the switch port command. There's plenty of switch port options, but the one we want right now is access. We'll talk more about access, trunk, and voice ports in the next video, but basically an access port has a printer, workstation, server, or some other end device connected to it. Access ports are the ones that you'll see the most often. So we'll finish up with access VLAN 10 and bring the port up. This puts the port in VLAN 10 as the command suggests. Of course, we need to set our 3 other ports in the same way. 1 more in VLAN 10 and 2 in VLAN 20. If we go back and look at our VLAN list again, we can see that VLAN 10 and 20 are now assigned to a few ports. If we move over to Workstation 1, we can test this with a tool called Ping. You may be familiar with this tool already, but we haven't discussed it before, so let me give you a quick overview. This tool is going to be your best friend. Ping sends a small piece of information over the network to an IP address. If the IP is reachable, the destination will send a small message back as a response. Have you seen the movie Hunt for the Red October? The captain uses sonar to ping the other submarine.
Verify our range to target. One ping only.
Aye, Captain.
Just like that, we're sending out our message, and if we see a response, we know that it's working. So let's ping workstation 2. We're getting responses back, which is great. That means our VLAN is working. What happens if we try to ping server 1? We don't get a response. But that is not surprising. After all, this is what we wanted. Workstations and servers are in different VLANs, and therefore they can't reach each other. But what if we do want them to reach each other? To join the two networks, we need to use our router. First, we have a quick look at the workstation settings. We can see here our IP address is 192.168.10.1. And let's have a look at the default gateway. That's not fitting on the screen very well. Just let me expand this and we'll try it again. That's much better. Our workstation uses 192.168.10.254 as the default gateway. This is our router, but we can't reach it yet as we haven't configured the switch ports that it connects to. So let's do that now. This is exactly the same as before. The router is connected to two interfaces on the switch. We need to put one into VLAN 10 and one into VLAN 20. Sorry, I've got this back to front. In this lab, GI01 is in VLAN 10. The router itself is already configured, so we won't worry about that right here in this lab. But is it working? Let's go back to the workstation to find out. To start with, we'll try to ping the router itself. And that's working well. Now we'll try to ping a server in a different VLAN. And that's good too. But how do we know that this traffic is actually going through the router and it's not some sort of switching trickery? Let me show you another tool. You may also have seen this one, but if you haven't, this is going to be your second best friend. It's called traceroute. This is just like ping, as it sends small pieces of information and it looks for responses. But it doesn't just test the end of the path, it tries to find each layer 3 device along the path. So what it will do is it will find the IP addresses of every router along the path from the start to the finish. And you can see here that our router is indeed in this path. If we wanted to, we could add some rules to the router to allow some traffic but not others. This is something we'll do in a few videos' time, so watch out for that one. Now, I want to give you a little bit of bonus information. You can feel free to skip this if you want to. Notice that when I use traceroute, the command has a -n. Do you want to know why? I use this to speed up traceroute. By default, traceroute tries to figure out the host name of every device in the network path. Our network is just not set up for this. So I add this -n to tell it not to bother trying to figure out the name of every device. Just give me their IP addresses. As you can see, without the -n, it takes a lot longer. And I mean a lot longer. Traceroute is trying to work out the names of every device in the path using a system called DNS. And that is something we'll cover later on in a different video. And if you're wondering, it's -n in Linux, but -d in Windows.
We hope you enjoyed the video and found value in the content. We value your feedback. If you have any questions or suggestions, feel free to post them in the comments section or contact us directly via our social platforms. Thanks for watching.